Thank you. All right, so we are recording for those at home, or in case you want to hear this again, I will get the screen share going. And we, last time, started looking at how to do things in SAS and Stata. So covered univariate statistics describing single variables at a time, and we're about to move into the world of bivariate statistics, so describing associations between two different variables. And rather than ask you the usual, what do you remember from last time, we can go through this example, and that will hopefully jog your memories and give you a little bit more specificity in what we've been talking about. It always helps me to see numbers anyway. So last time we rolled through some of the code here to import data. And just to remind you, the big thing to pay attention to is right here. So this is SAS code that I have highlighted. This is page 1 of example 2. That is where you will tell SAS where the folder is that holds your data file. So not the file name included, just the folder part. And it will use that information then in importing your data set. And for each example or homework, I will provide systems of labeling categorical variables, labeling all of the variables, and applying whatever formatting is necessary. And then in this example, I have proc standard is something to generate z-scores, examples of a linear transformation. You don't need to worry about that, but I have it in here. And for folks who are learning with Stata, the place to put your path is in this line right here, and the same thing will happen. It invokes that line of code as the address for where your file is located, and then the file name goes after it. So then we have the labels for the categorical values for the variables themselves, and giving your variable an STD by z-scoring it, giggle giggle. Making a log transform version, another thing you're not going to have to worry about. And then we started talking about the descriptives. So are there any questions or things you wanted to hear more about with respect to the code?
In the past, have students demonstrated a preference more for SAS or Stata while doing these assignments?
A few have. The ones that have expressed a preference seem to like SAS better because it's more explicit. But that might just be because I like SAS so much and there's a biased selection process at work. The only problem with SAS is that you really have to be affiliated with a university, and in particular a university in the United States, to use it, to have access to it. It's not something you can buy individual licenses for very easily, if at all, whereas Stata you can. So Stata may be a little bit more universally applicable in that case. And then, of course, there's the people who say, well, if you want universally applicable, learn R. And R is the least friendly of all of these packages. So I've opted not to go there for an introductory class, but that would be where you could go eventually to make sure that you always have access to software if you're willing to fight. So Stata is less typing, which makes it better for some folks, but less typing also means that what you're doing is more implicit and less obvious. So you really have to know what you're looking for, I think, to understand some types of Stata commands. Jin likes Stata better than SAS. Where'd you go? Oh, I lost his picture. He's hiding behind his dog at this point. I'm not going to yell at you for having a preference. I like Stata for some things too. I've gotten more used to it, and I appreciate certain features that you can do in Stata that do not have the same capacity in SAS, especially when we get to models. Stata has some very nice features that way. And he has been told apparently that he needs to learn Stata, and that is fine too. It has a lot of features. It has the same things with respect to people being able to contribute packages that R does. So you'll find people who've made Stata routines to do various things, and they put them on the web, and you can download and install them. And so it has a lot of those features. I like Stata. SAS has a special place in my heart. It just does. So, anywho, other questions about syntax or commands and importing data, variables, any of that? Okay. I know that that's not really what one thinks of necessarily when they think about learning how to do quantitative methods or learning how to do statistics, is focusing on software. But honestly, this is such an important part of the process, learning how to actually do things with data when the time comes. And it's complex enough and opaque enough that I want to make sure that we can go over it and have you understand what's going on with the packages. So I do think it is an important part of the process, even though it might not seem that way to start with. So we did proc means before to get univariate information for quantitative variables. Do you remember what it is if you have a categorical variable instead? How you would get univariate percentages, say, counts, that kind of thing? No, not off the top of your head?
Isn't there like a word you put between like max and data?
Yeah, last time I did do that. I added the word variance in this line so that you could get variance if you wanted instead of standard deviation. But I was referring to what you would do instead of this to get descriptive information for a categorical variable, because proc means is designed for quantitative variables. Proc something else.
Freak. Proc
Yeah,
freak.
proc freak for frequencies. So we'll see that later in this handout, because we'll be looking at that to get bivariate associations between categorical predictors as well, or categorical variables rather. And the analog to proc means or proc univariate in Stata is the summarize command, and you just list the variables that you want a summary for. I also found another option that's just mean, and that option gives you the standard error of the mean as well as a confidence interval around the mean. So I wanted to point out an asymmetry across programs and how you ask for things. So in SAS up here, alpha of 0.05 is telling it that for your confidence limits around the mean, that's what CLM stands for, that you want a 95% confidence, whereas that is specified directly in Stata. So rather than say alpha of 0.05, you tell Stata level 95, and it's the same idea. And so then it gives you the 95% confidence interval as well. And we went over this last time, but one more time, what's the difference between standard error and standard deviation?
Standard deviation, that's going to tell us how far away we are from the mean, and that's going to help us set the boundaries for our confidence interval. And then our standard error, I think that's when we're outside the confidence interval and we're unexpected, but I'm not as confident on that one.
Okay, so we got part of that. The first part worked. Standard deviation is how far on average any one person is away from the sample mean. That much we got. But then the boundaries of the confidence interval, that's not standard deviation, that's standard error. Yeah. So standard error then is what? Don't know. Okay, you're off the hook, Alex. You already answered one question. I don't want to cold call on anybody, but I will if I have to.
Okay, I'll try this one.
Okay, you go for it.
So standard error is isn't it how far away your sample mean is from the true population mean?
That's what standard error of the mean is, yes. So that's what we're talking about here. Yes. And so then that describes the expected inconsistency of your sample result across samples. So in this case, if we're talking about the standard error of the mean, it's just as you said, the difference of the sample mean on average, how far off it is from the population mean. And we could also have standard errors for any sample quantity that we come up with. So even though I know this may hurt your heads to think about, the standard deviation has a standard error. Right? Like if you think about your estimate of dispersion, right? A number that describes differences between people. That number is not going to be the same across samples either. So your standard deviation has a standard error to it. Your variance would have a standard error to it. Your skewness would have a standard error to it. Your median has a standard error to it. Everything does. And sometimes you can come up with the standard error with a ready-made, off-the-shelf formula, and other times it's not so easy. But for this context, there's ready-made, off-the-shelf formulas that your software will execute for you. And so then this standard error right here, for instance, for income, is what is used to create this confidence interval. And what is multiplied by the standard error is the t critical value that corresponds to your area. So if you want 95% confidence, 5% alpha, 95% expected, 5% unexpected, then that corresponds to a t with whatever value for the critical value that's given your sample size here. It's going to be pretty close to 1.96 because this is a very large sample. But you don't have to figure out what that is. It knows. Okay. Any questions on any of that? Yes, please.
Just to clarify, I want to make sure I heard you right, that standard error is the expected inconsistency across samples. Is that what you said? Okay.
Mm-hmm. And I say it that way because more is worse. So if you have a higher standard error, that means there is more expected inconsistency across samples relative to a lower standard error. And there's two things that go into standard error. One of them is sample size. More people, more consistent. So less variability across samples if you have a larger sample. And the other thing is the standard deviation. And if you have a sample that has more dispersion in it, that is going to create more inconsistency in what the mean would be in any one sample. So higher standard deviation translates into higher standard error. Higher people, higher sample size translates into lower standard error.
May I tack on another question to that?
Please.
So in my field, with the basis of what we do is single case designs, we have like really small population sizes, and I know we're supposed to be able, to prove that it's okay. We are supposed to be able to replicate that, across a lot of trials, or show how it can generalize into group design. So is that something we learn to do in this class, or is that something I haven't taken single case design just yet. I just know that's what we do in my field. So is that kind of something we work with in stats, or are they separate?
It is related, but the inference is different. So to you, then people would be observations. So if you measure a kid's progress, right, more observations helps you nail down better where they start, what happens to them after you treat them. If you remove the treatment and put them back to baseline, then in that case, your precision, your power, and your inconsistency, all of that is tied to the number of observations you would have for each of your n of 1 people. So same ideas. More is better. There's your take-home message, right? How much data do you need? More. How many subjects do I need to recruit? More. How many observations do I need to collect? More. Okay, thanks for the question. All right, other questions? Alrighty, then something new. I don't think we talked about this yet, right? Correlations. So here's SAS to start with, and then we'll do Stata. So I'm at the top of page 4 of example 2. Meet our new friend, proc core. Can you guess what core stands for?
Correlation.
Yeah, with 2 R's. So the proc works the same no matter what kind of proc it is in terms of how you write the code. first thing it's going to want to know, okay, what data set do you want me to do this for? So in SAS, you'll need to make sure that you have pointed it to the right data set. That means if you borrow this code to work on homework 2, you'll need to make sure to change this from example 2 to your title of your homework data set, which will be called homework 2. The keyword Pearson is actually a default, but I've put it here to make a point of it. What we're going to be asking for are Pearson correlations. There's about 8,000 kinds of correlations on Earth, and Pearson is one kind. That's the kind that we're talking about right now. Then this extra piece right here is allowing us to get confidence intervals around the correlation coefficients. And the Fisher keyword means what they're going to do for us is take each R, compute a Z value that goes with it, that nonlinear transformation that stretches R out so that it's not bounded. It's going to use, then get a standard error for that Z metric, get the confidence limits for the Z metric, and then back translate them into R for us. So all of that happens by magic with this additional option. Bias adjust is an option for whether or not you want the regular flavor Pearson correlation or the version that adjusts for the sample size. If you have enough people, they will converge onto the same estimate, but I went ahead and had the adjusted version in here just to show you what the difference would be in this particular data set. So we'll end up with both sets of results. And then this alpha equals 0.05 is again referring to what kind of confidence interval you want. So you're telling it to get a 95% confidence interval for the correlation itself. Then var, that refers to the names of the columns in the data set. So var in this instance stands for variable, not variance. And so I am asking for correlations among 4 variables simultaneously. So that's going to come out as a matrix. So each variable correlated with each other variable, and that is what this table down here is providing. And then of course, last but not least, run closes the proc so that it would actually go. And then title makes it so that this title that I've added as my trail of breadcrumbs in looking at the results shuts off after it's done, so that it doesn't keep printing forever and ever. Okay, questions on that code?
I actually do have a question about this.
Sure.
So I have like no coding background, so this might seem like redundant, but I am sort of confused about the use of the semicolon and specifically about when I need to start a new line of code after the use of a semicolon versus when I can just continue writing code on the same line, if that makes sense.
Yes, that is actually a great question, because that the when you need to make a new line thing, that is why SAS uses semicolons and Stata doesn't. So the concept in general is when you are writing instructions to the computer to do something, how does it know you're done? How does it know to stop reading and go execute whatever you've asked it to do? Some programs, you're done when the line of code ends. So like the physical line that you're typing into, when it reaches the end of any content, it stops and it goes. That's what Stata does. SAS does not do that. SAS instead uses the semicolon as the key to tell it, okay, this idea is over, on to the next idea. And then the ideas are connected to each other inside a proc and then sort of closed with run. So it's like a sandwich. It's like proc something is the one bread, run is the other bread, and then the middle are the commands. In SAS, I tend to make, in terms of like just visually, the reason that var is indented is because it's the inside of the sandwich. Like I keep the left margin for the outside and then the inside part is indented. But I don't have to do that. So SAS would have no problem, for instance, with me, let me just show you for a second, moving these to the same line, because this idea of which variables I'm asking for has been shut off with the semicolon, so it's ready for the next idea, and then when it encounters run, it knows what to do with that. Whereas if I tried to do something like this in Stata, it will give me errors, because when in Stata, each command has to be on its own line. And if you have a command that's long enough to where you need to literally wrap it around, like you run out of room, you actually have to put a special character. It's 3 slashes to tell it, no, don't stop reading when you get to the end of the line. Keep wrapping around and keep going. So that's actually a really great question because every package does it differently. And so in general, packages that are line specific, they don't require anything at the ends like a semicolon, whereas packages that you can string things together on the same line, you can use semicolons to then tell it apart.
Okay, so that makes sense. So what you're saying is that SAS is not, as you said, line specific.
Mm-hmm.
Okay, so you just need to have the proc and then the run and the semicolon after the run to like have that all the sandwich make sense.
Yeah, so each, like this is sort of the introduction to the sandwich, and then each like sub command, some sort of option within it has its own semicolon, and then the run has a semicolon as well, because those are 3 different things that work together.
Okay.
And I write them on 3 different lines to sort of emphasize that they're 3 different things, but I wouldn't have to. I could string them all on one line if I wanted to. Semicolon is the crust of the bread. Yes, except then you'd have crust in the meat also. So I'm not sure where the analogy starts to break down, but the proc sandwich idea holds. In general, if you forget a semicolon, what will happen is that the words after it will be colored wrong. So like if you're looking for your run and it's not blue, then odds are very good that you forgot a previous semicolon and it thinks run is part of the previous command. So in SAS, you can use the colors to help you. Things that are dedicated SAS commands will show up in some sort of blue, and if they don't, something is off. If you ever see red, something is wrong. So it knows whether or not you're writing inside the sandwich or outside the sandwich. Stata commands are also blue, but there's not as many varieties of colors. Sure would suck if you're colorblind. Inside the package, though, you can tell it which colors you want it to use. So like if you had a sensitivity, you could actually change it so that red was good and blue was bad or something like that. But all right, good questions. So proccore in SAS, and then I've got a bunch of output here and pictures. We'll go over that in just a second. But just to give you a sense of what Stata's version of it is, it's just that one line. So this is on page 6. The Stata command to do the exact same thing is pwcore, which stands for Pairwise Correlations. And then you list the variables that you want to correlate. The comma is used to shut off the list and then transition into options for what is going to be displayed. So this structure where you have do this, comma, after the comma are always some kind of option. And sig means print the p-values. I don't know why you wouldn't want that. And obs means tell me how many observations were available for each pairwise correlation. And then we end up with a table that is very much the same as what SAS gave you. So we can look at that up here to start with. Okay. So in this data set, I have already sub-selected the sample so that everybody has every variable that I would use in these examples. And so that's why the N is given in SAS at the top of the table. In real data, if not everybody has every variable, by default, it will use whatever cases it can, but then it will give you the N for each unique combination. So like for these two together, it would have an N here and an N here and an N here. Okay. So to look at this table, so this is a matrix where we have 4 rows, 4 columns. It's what's known as a square matrix, meaning that half of it is redundant. So on the diagonal, so this cell right here, this cell right here, this one, and this one, that is the correlation of each variable with itself, which should be perfect. So that's why there's 1s on the diagonal. The other cells, so this chunk right here, this chunk right here, this one, these are what's known as off diagonals. And the off diagonals below the 1s are the mirror image of the off diagonals above the 1s. So for instance, the correlation between education in the 4th row, 1st column, and income of 0.38 is exactly the same information that's given in row 4, column 1. Okay, does that make sense? It's the same thing twice. So in practice, when you're reporting this type of correlation matrix in a paper, you would typically only give the top half or the bottom half, but not both. So the lower triangle, if you picture this sort of with the ones as the edge of the triangle, it would either be like these 6 values down here and these would be blank, or vice versa. Sometimes you'll see it if you have maybe 2 groups of subjects. You might report the correlations for one group below the diagonal and the correlations for the other group above the diagonal. That way you save space. So the values in here, the first number in each little chunk here is the value of the correlation coefficient between the 2 variables. So that right here, for instance, is an R. So this pair of variables is correlated 1. These variables is original income and z-scored income. Is it surprising that income and the z-scored version of income are perfectly correlated? Not surprising at all. Why is that?
The income Z is just a standardized version of the income. Yeah.
Exactly. Income Z is a standardized version. More specifically, it is a linear transformation. So all we've done is take income and rescale it to have a mean of 0 and a standard deviation of 1. It does not distort or change the information in any way. It just puts it on a new metric. So that is why these 2 variables are perfectly correlated. In contrast, if I go down here and look at this one, 0.82 is the correlation between income and natural log transformed income. Now, what does that tell us? Are they the same thing? Yeah, not anymore. So a natural log transformation is an example of a nonlinear transformation. It puts the variable on a different scale, but it does so unevenly across the values. And in particular, I think I have a picture of this. Yep, I made a picture just to show you. This is the relationship between original income and the log transformed version. And so the straight line here is what the Pearson's correlation is trying to pick up on. Pearson's correlation is an index of a linear relationship, linear. And clearly these variables are related, but they're not related linearly. They're related exponentially. So that type of curve has a special name, and that's what a log transform does. It reels in the values that were at the high positive end, and it spreads out the values at the low negative end. So in the new log transform metric, there's not as much of a difference across people and income as in the original. So oftentimes people will log transform variables that are positively skewed to reduce the impact that extremely high positive values would have on the degree of association. So this correlation right here is not perfect, it's 0.83, but this also helps to illustrate that Pearson's correlation is a very specific kind of association between variables. It is a linear association that it's indexing. And if variables are related non-linearly, like this one, it's not going to pick that up. But I'll show you how to do that. Okay. All right, so income and natural log transformed income are only related 0.83 because it is a nonlinear transformation. So just to make that as a point. The value underneath it, though, any guesses as to what that number represents?
The p-value?
It is the p-value. So p is less than 0.0001, which means what? There's a variety of things you could say about this.
Significant finding?
It's significant. What else could we say?
There's like a 0.01% chance of making an error.
close. There's a 0.01 probability of finding a correlation of 0.8, this extreme, if what is true? What do I have to say is true to make that sentence complete?
The null hypothesis?
Yeah, the null hypothesis. Now, what's the null? We didn't tell it that. It picked one for us. How convenient. Is there any information on this page that is telling us what it is using as our null hypothesis? Let me see if I can make this bigger. It looks like some of you are squinting at your screens. We don't want that.
So the null hypothesis says that the correlation is 0.
And where are you seeing that?
It's on the text box on to your right.
Yeah.
But it
Yeah,
also
I
says
wrote
it,
that.
it also says it right above all the data where prob greater than absolute value are under null hypothesis
Yeah.
correlation 0.
That. So this is what the SAS programmers thought would be useful to you. And this text box over here in a different font is Proc Lisa. This is me earning my salary. Let's try and decode what they're telling you. But yes, the probability of R with the bars around it, that means absolute value. So it doesn't care whether or not it's a positive correlation or a negative correlation. The significance test would be the same. We're using a two-tailed test because SAS doesn't believe in bullshit voodoo either. Under HO, which stands for null hypothesis, and then rho equals 0, rho is the population correlation notation. That is the Greek letter that actually looks like a P. And so I guess they didn't have Greek font as part of their initial choices, and so they wrote it out as rho. So yes, if you wanted to change the null hypothesis, let's say that you had some reason to believe that a correlation between two variables should be 0.3, and you wanted to see if your correlation was different than 0.3. You can actually do that. I don't have that in here because it was confusing students when I had it before, but that's an option that you can put inside this set of parentheses here to change the null hypothesis, and it'll give you additional output relative to that as your new null. If you pick a correlation that is not 0, that is what's known as a non-nil null. Yeah, I can't make this stuff up if I tried. But yeah, it's picking 0. So then putting this all together, each of these little numbers underneath the correlation that say, in this example, less than 0.01, that is the probability of getting a correlation that large or larger if the null hypothesis is true. So if these data came from a true population where these variables are unassociated, you would only see a result this extreme less than 0.01% of the time. So way unexpected territory. Significant is another word that we could use. And there's one more. What would we say about the null hypothesis? I'm taking
reject the null.
Reject, yeah, reject in capital letters. Big time reject. Yeah, you're not supposed to say things like really significant because significance is supposed to be like a yes or no thing. But yeah, this is really significant. Big time reject the null. So if I were writing this up, which by the way I did for you, let me scroll to that so that you can see it. Just a moment. Here, this is on page 6. Some words. So for every example that I'm going to give you this semester, I'm going to give you a write-up as to how I would actually talk about this. And so I would describe that correlation as significantly positive. Significant because it would happen with a probability of less than our chosen alpha of 0.05. Positive because that's the direction of the relationship. So it is unsurprising that a variable and a variable that has a natural log transform would be related to each other. So really the only part of interest in this table is these two correlations right here, which is the relationship between income and education. So what would these correlations imply about the association between education and income? Correlations of 0.38 with the original z-scored version and 0.30 with the log version.
Like low positive correlation?
Yes, small-ish. I actually, depending on your discipline, is what big and little is, but relative to what the highest possible correlation could be, which is 1, and 0 meaning there's no relationship, this is a relationship of 0.3, 0.4, so it's, you know, small-ish. So more money is related to more education to some extent, we would say. And what might be noteworthy about both of these things is that the relationship is still basically the same size, a little bit smaller, but not by much after you do the log transform, meaning that it's not the people making big bucks that are causing this relationship. So you can think of this as kind of a robustness test. That phrase is used to, like, when you kick the tires to make sure that you'd still find the same general tendencies if you did it this way or that way. So the fact that income and education are related is not due to those extreme observations that have a lot more income than everyone else. All right. And what is not available on this printout, by the way, which I've highlighted over here, is the test statistic. So what they don't give you is the intermediate quantity that generated these p-values, which is t. So if you know R and you know your sample size, that leads to the t-test statistic. These p-values correspond to that t-test statistic. So they don't give them to you because they don't give you any additional information. So just know that that's the intermediate step that they skipped over for you. All right, how are we doing? Good, all right. So then the rest of this little table right here, this is the additional output that was generated by this Fisher option specifically. So this is extra stuff that I asked for to show you the results of the Fisher nonlinear R to Z transformation that is used under the hood to compute confidence intervals. So in this table are every pairwise correlation of the 4. So because there's 4 variables, there's 6 possible correlations. So for instance, if I look at the last one here as a point of reference, the correlation computed between these two variables originally is 0.30. And if I were to adjust it for sample size, so there's a formula by which you can recompute the correlation adjusted for sample size. The adjusted correlation is 0.31, and the difference between those numbers is given, actually, sorry, this is the Fisher Z version. The adjusted correlation is over here. So because we have such a huge sample, it's not adjusted by much. Fisher Z is the result of the nonlinear transformation of this number. So if we look at this correlation up here, a correlation of 0.82 corresponds to a Fisher Z of 1.1. So this picture right here describes the mapping of those two variables, where R is the x-axis and the transformation is the y-axis. So it takes a bounded correlation metric and stretches out the ends so that you can use that new metric to compute confidence intervals with. And so then it does all of that for you. So here's the confidence interval around that correlation estimate. So this is what I would report in addition to the estimate to try and help your reader understand just how noisy that correlation estimate would be expected to be. So just as we have a standard error of the mean that describes the expected inconsistency across samples, confidence intervals around the correlation help convey the expected inconsistency as well. So you can think of this as like 0.30 is what we got, but across 95% of the samples, the true population correlation would be somewhere in here. That's what it means. And what happened under the hood, the Z steps are given in this section of the handout here. So first step is to take R and turn it into a Z. The adjusted R is given here, and then compute the boundaries of the confidence interval in the Z metric, and then back transform into R. So all that stuff happens for you and shows up in this little table right here. Ta-da! So, questions on that? So the only things that would be of interest is this as what's known as the point estimate. So that's the correlation that was obtained in your sample, adjusted for sample size, and the confidence interval around it is that. So those are the two things that I would report in addition to the p-value that was up here in this table right here. All right. And then pictures. So proc SG plot is what I use to make this scatter plot. This is not something I need for you to do. I just wanted you to see it. So in case you ever want to make pictures, SG plot is a general command that has all kinds of different pictures you can make. So this is generating a scatter plot for these two variables and then the regression line that goes with them, just so that I could show you what a nonlinear transformation looks like. And here is what the scatter plot looks like for education and log income. So the slope of the line conveys the strength of the correlation, but here in this case you can see there's a lot more noise around it. So that's a correlation of 0.30, I think, because even though we're sort of heading up in general, there's a whole lot of noise. It's a lot harder to see what the correlation would be without this line superimposed on it. All right, Stata folks, your table is very much the same with the exception of the sample size being embedded in it. So the top value is the correlation. The second value is the p-value, and note that rather than saying less than 0.0001, it reports it as 0. It is not 0. P cannot be 0, so never ever say that it's 0. When you report it in text, you would say it's less than 0.0001, because if you went out enough decimals, you would find a value there. So it has to be some positive number. But otherwise, they all agree. And then I tried to find out how to get Stata to give me the confidence intervals and discovered that someone had written a little package to do that. So it wasn't built into the core of Stata, but I found it thanks to Google University. So there is a package called CI2 that I told it to go and install. And this is something that even if you don't have administrator privileges, you can do on your machine, by the way. I checked. So you can run this on virtual desktop and install these additional packages as needed. And then CI2 is the commands. You would give it the two variables that you want to compute a confidence interval for, and then the metric you want, whether it's a correlation or a covariance. And so then that little command spit out that text for me. So I would have to do this 6 times to get every possible pair of correlations. It won't let you stack them up, but at least then you can get the same information. This is unadjusted though, so it doesn't do the adjusted for sample size version. It only has unadjusted. So because of the differences between packages, I don't think I asked for this in your homework. But just so that you would know how to do it, and then here's how to make the same scatter plot pictures. I found Stata code to be able to do that. All right, so any questions on concepts, code, any of that?
I just can't believe folks used to do this without computers once upon a time. Like, I can't fathom.
Yes, we are all very lucky that these things take fractions of a second, what used to take weeks or years to do by hand. Indeed. All right. Okay, yeah, so then we're ready to go back to other kinds of correlations. So are we good with this? Good with this? All right. Then let me go back to our lecture and talk about other kinds of correlations that you will get a chance to practice or encounter in your lives. We find where we are. Pearson's correlation. Yes. So picking up on lecture 2, slide 22. The idea of what Pearson's correlation actually indexes is a linear relationship. So in the data that I had made up for this example, I had a correlation of 0.99 between height and weight, and this is 10 observations that were generated from a population with 0 correlation, and so in this case I have a negative correlation that was non-significant. But Pearson's correlation is not going to tell you the full story or the right answer if you have 2 quantitative variables that have a nonlinear relationship. So something like this, for instance, this is what's known as a U-shaped relationship. You might also describe it as a quadratic relationship or a parabola. And what this scatter plot would seem to imply is that at lower values of x, there appears to be a negative relationship, right? Like if I took a line and tried to fit it through this side of the plot, then higher values of x correspond to lower values of y. And after a certain point, that trend reverses to where higher values of x correspond to higher values of y. If I just asked for a Pearson correlation between these 2 variables, the line would look something like this, and that would correspond to a almost 0 correlation, but that misses the story. So when would something like this happen? Can you think of any examples from your research or your life that would describe a relationship like this? I can. Performance and arousal. So if you have something to do that's important, a sporting event, a dissertation proposal defense, something like that, right? Like the best place to be is like alert, awake, excited, but not super freaked out, right? If you don't care very much, poor performance. If you care too much and you're psyching yourself out, poor performance. There's a sweet spot in the middle. I think there's a lot of variables in the social sciences where more isn't necessarily better. They may not switch direction in terms of the relationship, but it may level off. And so to the extent that you have any kind of non-linear association, Pearson's correlation isn't going to pick that up. And so here is a very famous example of that. Somebody generated 4 different types of data, each of which has a correlation of 0.82 in it. So in the first cell here, the top left, this looks like the line does a good job of describing the relationship between these variables. They do appear to be strongly positively linearly related. Over here, the line misses. So there is a relationship, there is a functional form, but it looks more like this quadratic U-shaped form than linear. Over here, there would be a perfect relationship if not for this guy. Some rando messed up my line. If they were down here where they're supposed to be, then the line would be perfect. And then over here, there is no relationship except for that rando. That one extreme value drug the line clear over to themselves when it really shouldn't be there. So this is to say there are many ways that quantitative variables can be related. A Pearson correlation is a linear relationship. If you wanted to be able to test quadratic relationships, curvilinear relationships, and other things, you need a model. So that's the very next unit is getting into modeling, where we will learn how to actually predict quantitative outcomes from quantitative or categorical predictors and include the potential for nonlinear effects of various kinds. So that's getting it started with that as lecture 3, and the nonlinear effects show up in lecture 4. So we'll get there very quickly. All right, so questions, thoughts? Good so far? Good still, I should say. Good still. All right. So other words that you may have heard or may hear in your life that I want you to be aware of. Pearson's correlation has two other names that get used for certain combinations of variables. So we had talked on Tuesday about binary variables as a special case. Binary variables can be treated like quantitative variables. So if I had a correlation, say, between whether or not you're in group A or group B and income, I could do a Pearson correlation with that. I know that sounds sort of crazy because you think about the idea of a line, but being higher on X and higher on Y, you can use that language in the context of a binary variable. You would just have to know how it's coded. So if I had a binary variable for group, I've got group A and group B. If group A is 0 and group B is 1, then that means being higher on that variable is you're in group B. So if group B had a larger income than group A, I would see a positive correlation between group and income. If group B had a lower income than group A, I would see a negative correlation. So you can have Pearson correlations between binary variables with each other or binary and quantitative variables, and these have special names. So a Pearson's correlation, if it's computed between two binary variables, is what's known as a phi correlation. And if it's a binary with a quantitative, it's known as point biserial. So these are synonyms. It is the exact same damn thing as a Pearson correlation. It's just that there's a computational shortcut to the formula that you can use if it's binary. So these are just the same thing reworded. What isn't the same thing, though, is a correlation made up by a different old guy and named after himself, which is Spearmint. So another kind of correlation coefficient that you'll get a chance to practice with in homework is the Spearmint correlation. And what it is designed for is either ordinal data, where the numbers aren't really numbers, but you can pretend like at least they're in the right order and have that mean something as to what higher means, or for quantitative variables where you are sort of suspicious of higher cases and you don't want to give them weight. So like if you were worried about, that guy over here dragging your correlation, Spearmint could help you. So the way that Spearmint correlation works is entirely as a data transformation exercise. What happens is that you take your quantitative variable and you convert it into a rank order version. So the lowest score is 1. The next lowest score is 2. Doesn't matter how far apart they are. It's just what place did you finish, so to speak. So if you have, say, a Likert scale, and remember it is Likert, not Likert. A kitten dies every time someone says Likert. Then your data already look like that. So you have 1s, 2s, 3s, 4s, 5s probably, and it's fine. Otherwise, if you have a quantitative variable, if you convert it to a rank order, then do Pearson correlation. That's Spearmint. It's exactly the same formula. It's exactly the same process for testing significance using a t and then the p-value that comes with it. So it's just a data transformation first. And you can do it with inside proc core, which I'll show you with the keyword Spearmint, or Stata has a command called Spearmint. And yes, me typing in capital letters, by the way, to reference Stata commands is me trying to stick it to the man who insists that they go in lowercase. So that's just, I'm just being ornery. But I tend to like to write uppercase to sort of emphasize that this is a program specific thing and not an English translation of it. Like you have to type it exactly with the spelling, for instance. So these pictures sort of illustrate the difference in when you would expect a different result from Pearson versus Spearmint. So the first picture here, there's not really any extreme values, and the Spearmint correlation and the Pearson correlation would be pretty much the same thing. In this picture here in the middle, Pearson correlation, the line would try and draw a line between these two things, and it's not going to be perfect. Whereas if you do Spearmint, then all of these values down here that get further and further apart, they get shoved back up because they're just next, right? The distances between them are squished. And so these tails here, once you compact them, then it ends up that they're all on a straight line again. And then over here, we would have a larger correlation for Spearmint than Pearson, because again, these guys that are far away would just be next in terms of the rank order, and so the distance would be squashed. And so these yellow dots then would end up looking closer to the line, and the line would fit better as a result. So take home message: if you have data that are ordinal, variables that are ordinal, or you are worried about the influence of extreme values for your correlation, Spearmint is a way to go ahead and make sure that you can get an association that is somewhat protected from those potential problems. All right. Do you want to see how to do it? Okay, I'm going to play Where's Waldo? Find the difference in the code that gives me a Spearmint correlation instead of a Pearson correlation.
It says Spearmint instead of Pearson.
Ding, ding, ding. Yep. And you can actually get both at the same time. So Pearson is provided by default. Spearmint is not provided by default, so you have to write it down. But in your homework, for instance, I will ask you to look at the same correlation both ways. You can get that out of one analysis. So the same idea of getting the correlation, getting confidence intervals around the correlation. Literally the only difference is the data transformation step that happens ahead of time. It does it for you. So it doesn't do anything to your data set. It just converts the rank orders internally and then gets the Pearson correlation on the rank order data. One nice thing that it does in terms of descriptive statistics when you ask for Spearmint correlations is that it also spits out the median. So for these two variables right here that I'm going to use in this analysis, so I'm using the original income variable, friends and happy were ordinal variables. So friends was how frequently you see friends and social settings on a ordinal measure of 1 to 7, where I don't have to remember what 1 to 7 means off the top of my head because that's what this is for. So these are value labels that you can assign to your variable. That way they're tied to it in the data set. So 1 is I never see friends and 7 is almost daily. So this is an example of they're not really numbers, right? They're numbers in the sense that almost daily is more than several times a week, which is more than several times a month, but the numbers per se don't mean anything. Likewise, for this happiness, this is a 5 category. How happy are you? I'm not happy, all the way up to completely happy. Not really numbers. Okay, scrolling back to where we were, 1 second. Sorry for the vertigo. But if I look at the descriptive statistics, what kind of distribution do you think that this friends variable has? Do you think it looks skewed or not skewed?
I think it's skewed.
Which way?
It would be positively skewed.
Yeah, the mean is above the median, so it's being dragged. Let's go with dragged. See, this is what happens when you become fluent in toddler. You forget basic English skills because he says things like drugged or dragged. So yeah, I'll go with positive. What about this one? What kind of distribution do you think this one has?
Negative.
Yeah, the other way. The median is 4. The scale only goes up to 5. How could the middle be 4? Because everybody lied. Everybody is completely happy or extremely happy or whatever the hell 4 and 5 mean. So whether or not self-report data are trustworthy is a whole nother class, right? That's a whole nother thing about research design and survey methodology and how you word these questions to get people to use the numbers appropriately. That's a whole nother class. I'm just dealing with the numbers and praying that they actually mean something. But yeah, so these are ordinal variables that are likely not that symmetric, although friends is likely to be more so. So we can ask for then Spearmint correlation. So that's how you know which is which. Your output table will tell you whether it is a Spearmint or a Pearson correlation. And if we look at this result right here, that is the correlation between annual income and your time spent with friends. So what is that telling us? The correlation coefficient is negative 0.05.
There's not much of a relationship, but it's slightly negative.
Not much of a relationship for sure, because it's pretty close to 0. It is slightly negative, so how would we put that into English? People who make more money. Go ahead.
The more money you have, the less you see your friends.
Yep. Or the less you see your friends, the more money you can make. Causality is not this class either. These are just associations. But yeah, so this is a negative relationship. It's pretty small. Here's my p-value. So probability of finding a relationship of minus 0.05 or bigger, if the true null hypothesis is 0, that probability is 0.21. So what labels then do we attach to this finding based on that p-value?
Not significant.
That's one of them. The correlation is not significant, meaning that it is not different than 0. What other words?
Go ahead, Doris. Yeah, that's my bad.
No, you're fine, Alex. I don't, doesn't matter. I was just going to say that we would retain the null hypothesis.
Retain or do not reject, depending on who your stats teacher is. But in a manuscript, we don't ever talk about the null hypothesis. We would just say this is a non-significantly negative correlation, or just the correlation is not significant. I usually like to keep the direction in there, even though it's not significant, because I feel like that is useful information to have. Although some purists would say that if it's not different than 0, then it's 0 and direction doesn't matter. But so this correlation is tiny, but the p-value is still like, it's 20%. What would it take to take that correlation and make it significant? Could I do that? Maybe. Under what circumstance could I get a correlation that small to be declared significant? P less than 0.05. What would I need?
Increase sample size.
That's it. The p-value is a direct function of R and N. So for the same R, having more people makes it easier to clear that significance hurdle to cross over into unexpected territory. And so this is the rationale by which the article that's on your reading list for this unit, The Earth is Round, P less than 0.05, if you have a big enough sample, everything is significant. So just knowing that I have a significant correlation does not tell me anything about how big of an association that actually is. If I had enough people, I could get a correlation that is this tiny to be different than 0. And then sure enough, you'd end up with like People magazine or someplace like that, running some headline, people who make a lot of money don't spend time with their friends. And then, we'd have some psychologist on there to talk about their research, and they would totally, misrepresent the size of the relationship, right? That's the kind of stuff that happens. So it's always important to think about effect size, which is given directly by the correlation coefficient, in addition to, and perhaps even instead of, the p-value that goes with it. So both of those things show up at the same time. What about money and happiness? Does money buy happiness? That's the other headline in Psychology Today, right? Money buys happiness, p less than 0.05. How would we describe this relationship?
There is a non-significant positive correlation between money and happiness.
Yeah, so people who make more money rate themselves as happier. A little tiny, tiny bit, but again, not significant. What about this one? Friends and happy. People who spend more time with their friends, ... So what I'm trying to do here is to get you from the generic language as, okay, this is a positive correlation, so as X goes up, Y goes up, and into the story. So people who spend more time with their friends, that's as X goes up,
Are happier.
rate themselves as happier. So that's the positive correlation idea, significantly.
Yes.
So what do I have to know ahead of time to judge whether or not I call that significant?
Confidence interval or your alpha value.
That one. Yeah, alpha. So alpha is something you're supposed to decide on ahead of time what your cutoff is. So the cutoff, if it's 5%, and by the way, it is less than 0.05. So if you got a p-value of exactly 0.05, that would be non-significant. Yeah, so because this is 2.5%, that would fall into the tails we've defined a priori. So yes, this is a significantly positive relationship. People who spend more time with their friends report themselves as being happier. So should you ditch your class and just go hang out with your friends on Tuesdays and Thursdays? Is this a compelling relationship? I thought you guys were my friends. This is like week 4, right? We're just partying together, talking about SAS output. That's what I do with my friends. Hell, that's what I do with my husband.
I mean,
This is like dinner conversation at our house.
I'm digging our time together, but you know.
At least you're getting your steps in while you get your requirements met. But yeah, the point I'm trying to make here is that this is not a large relationship. Even though it's significant and is unexpected, that is largely a function of the fact that I have 734 people here. That is not a big effect size. So what is a big enough effect size is entirely context specific. If I'm talking about associations between self-report data, that's not a very big effect. If I'm talking about, COVID vaccines or aspirin to prevent heart attacks or something, even the tiniest little help is a good thing. So I can't tell you what is important and what is not, but what I can tell you is that that thing is pretty close to 0. So, and another way of saying that an effect is non-significant, such as this one, is that the confidence interval overlaps 0. So not significantly different than 0 and having a confidence interval contain 0 are telling you the exact same thing. The p-value is just a more specific version of it, because in or out of the confidence interval is a very coarse distinction, whereas the exact p-value tells you with more specificity how far out you are. So the first 2 confidence intervals include 0, meaning that the correlation could have been negative, could have been positive, don't really know. Whereas the last one excludes 0, but just this much. So just that much. And here are some more words, because I want you guys to like me, even if we have to be here together. Stata, very similar. To get the same median lumped in with my descriptive statistics, I found another thing called univar that somebody made, so I got that. I got the same information. And then Spearmint is the command in Stata to get the Spearmint correlation. You tell it what variables you want, and then a little bit different looking options under stats. Row is, what is that? I'm going to go with the correlation itself, because Spearmint's correlation is labeled as row rather than R, because, you know, why not? And then observations is N, and then P is P. So the exact same information in the same little table, and then I did a R to Z transformation to get the confidence intervals for the last, or for one of them anyway, for the income and friends. So that's that information. All right. Ta-da! Questions?
I've seen in some papers like reported trending towards significant. What are your thoughts on that like argument?
Oh, there are so many euphemisms for that. There's actually a list I found on Facebook that had like 100 of them that they had found. It's cheating. It's alpha dodging, right? You really, it's so close, but you just, my favorite, by the way, is that it's approaching significance, because it makes it sound like a cake. Like if you just came back later, it'd be significant. You just haven't waited long enough. Yeah. So no, you got to get off the fence. So that's what I think. And I have the same opinion, by the way, about stars and crosses and tables, where it's like 1 star is P less than 0.05 and 2 stars is less than 0.01 and 3. No, it's just yes or no, up, down. I think that the gradation of how strong the effect is carried in the effect size. The p-value is just a marker for whether or not you get to talk about it. So I would discourage the trending the language that goes with it. So, other questions? All right, then that is it for today and this week. Let me know if you need anything as you get rolling on homework 1. If you get stuck, office hours start at 3:15. So otherwise, have a good weekend. Stay warm. Bye, everybody.